Hello everyone, I welcome you all to Physics Wallah, and in this session we are going to discuss the next as well as most important lecture related to our very interesting chapter, which is redox reaction. And basically in this session we are going to discuss about different type of concepts related to this interesting chapter. So basically our main focus will be on the calculation of a valency factor, or you can say N factor, and to understand the basic idea about redox titrations as well as your acid base titrations. Okay, and the topics which we are going to discuss in this session are basically first part, which is your valency factor. Then we are going to discuss about the concentration term, which is highly specific in case of redox reactions, that is normality. Then we are going to discuss about the acid base titration, and last part will be your redox titration. Okay, so this session is going to be very interesting related to the numerical analysis as well as the calculation part of equivalence. Okay, now let's talk about the basic idea about the valency factor. We were talking about the valency factor in the previous session also, and in that case generally for different type of species valency factor can be calculated differently. If I talk about the elements only, I told you that in case of elements generally the N factor is generally the valency of that particular element. In case of ions, N factor is nothing but the charge of ion. In case of species oxidizing agent or reducing agent, in that case N factor is basically number of electrons lost or gained by 1 mole of that species. So that part we have already covered. Now for simplicity, let's say we are talking about the concept that in case of acids, so in case of acids, always remember N factor depends upon the type of reaction. So N factor is going to change. So in case of acids, generally we know that N factor is nothing but the basicity of that acid. Basicity means number of H positive or number of moles of H positive given by 1 mole of that particular acid. That is the basicity. So N factor will be the basicity of the acid. If I talk about HCl, I can say N factor will be 1. In case of H2SO4, if it is given alone without any reaction, then 2H positives are there. So you can say N factor will be 2 in this case. In case of H3PO4, we know that N factor will be 3 in this particular case. Now there are certain things which are actually confusing in nature. For example, if I talk about H3PO3, in case of H3PO3, we generally think that it's going to give 3H positive, but that depends upon the structure. So phosphorus acids have general structure like 1 double bond, 3 single bonds. So if you draw the structure, that will be O, O and O. 3 oxygens are there. Now you can see one hydrogen is there, one hydrogen is there, and one hydrogen is directly attached to phosphorus. Those hydrogens which are actually attached to oxygen, they can actually lose in process of ionization, you can say, but the hydrogen which is directly attached to non-metal, it's not going to participate at all. It means 2 hydrogens are there which are ionizable. It means its basicity in that case will be 2. So N factor for this part will be 2. I hope this part is clear. In the same way, if I talk about H3PO2, again students think that this is going to give 3H positive, but again that depends upon the structure. Phosphorus double, single, 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 that is the skeleton structure. In that case you can see one oxygen and one oxygen, only 2 oxygens are there. Remaining part is hydrogen, hydrogen, hydrogen. Now those hydrogens which are directly attached to phosphorus, they are not going to participate in the process of ionization. It means its N factor is going to be 1 only. Now the most confusing one among these is basically H3BO3. H3BO3, which is your boric acid. Don't get confused whenever it is written as H3BO3 or BOH thrice, both are same. Both are actually same. So don't get confused. Now this particular part is not going to give any H positive, first of all, because it's already electron deficient species. You know, this species is already electron deficient in nature. This species is electron deficient in nature. So it's not going to follow the normal Arrhenius theory. So there is no concept of H positive. But in that case, we know that this particular part is a Lewis acid. This part is a Lewis acid because it's electron deficient in nature. So what happens? It's going to react indirectly. It's going to give H positive indirectly. What happens? It actually reacts with water and eventually it forms BOH 4 negative by accepting OH negative from water and indirectly releases H positive inside the solution. So in aqueous solution, it indirectly gives only one H positive, 1 mole of H positive. It means its N factor will be 1. So it's a weak monobasic acid. And which type of acid? Generally Lewis acid. I hope this entire part is clear. So it's a very interesting theory related to the boric acid part. Now, for example, I told you that N factor always depends upon the reaction. N factor always depends on the reaction. Always remember, it depends upon the reaction. So for example, what we can take, okay, for example, let's say I'm using H2SO4 with NaOH, okay, and in this reaction it's going to form NaHSO4 plus H2O. Okay, there is one more reaction which is H2SO4 plus NaOH. It's going to form Na2SO4 plus H2O. If you balance this, that will be 2H2O only. Okay. Now there is a difference between these two reactions. And if I talk about the N factor and you say that N factor in both the cases is 2, then you are absolutely incorrect. In first case, H2SO4 is only going to lose 1 H positive. So only 1 mole of H2SO4 is going to provide 1 mole of H positive in this reaction. So for this reaction, N factor of H2SO4 will be 1. But in case of second reaction, H2SO4 actually given out 2H positive inside the solution. It means its N factor will be 2 in this particular case. So that's why N factor is a reaction dependent. Always remember this particular part. I hope this entire thing is clear. Just note down this entire point, then we can proceed. I hope this part is clear. I hope this part is clear. In the same way, if I talk about the next part, which is N factor for bases. In case of N factor of a basis, how you are going to calculate? Again, that depends upon the acidity. So N factor will be acidity of a particular base. Acidity of a particular base. That depends upon the acidity of a particular base. Means how many moles of OH negative ion are given by 1 mole of base according to Arrhenius theory. So in that case, if you look clearly, let's say I have NaOH individually. So I can say its N factor will be 1. In case of, let's say, MgOH twice, I can say its N factor will be 2. In case of, let's say, AlOH thrice, or I can say FeOH thrice, in that case its N factor will be 3. And again, that depends upon the type of reaction you are performing. Let's say in case of NH3, what will be the N factor? So again, this NH3 contains one lone pair. So this species is electron rich species. It means this species is Lewis base. So I cannot define it according to Arrhenius theory. But indirectly in water, what happens? It's going to react with water and it's going to form NH4 positive and indirectly give 1 mole of OH negative. So again remember, in case of ammonia, its N factor will be 1 when it is acting like a base. I hope this part is clear. I hope this part is clear. This is the basic portion related to the entire portion. And again, that depends upon the type of reaction. For example, in case of MgOH twice, if only one OH negative will be given in the reaction, then its N factor will be 1. If both OH negative are utilized, then N factor will be 2. I hope this part is clear. Just have a look at basic idea about the N factor for bases. Now there might be a chance that we have a certain components which can actually act as acid as well as oxidizing agent. For example, if I talk about H2C2O4, in case of H2C2O4, which is oxalic acid, it can act as an acid, so it can give 2H positive and form C2O4 2 negative. So in a reaction, if it's going to lose 2H positive and form this particular part, then it is acting like an acid. It is acting like an acid, and in that case, its N factor will be 2 always. Will be 2. There might be a possibility that in a given reaction, it is going to be converted into CO2. If the final product is CO2, it means this carbon which is present in plus 3 is going to be converted into plus 4. It is going to oxidize. That means in this particular reaction, it is acting like a reducing agent. It is acting like a reducing agent. Now in this particular case, its N factor will be change in oxidation number, which is 1, multiplied by how many atoms are there? 2. So that will be 2 only. Okay. So in both the cases, whether it is acting like an acid or reducing agent, in both cases, the N factor will be 2. Now that depends upon the composition. For example, I have a species which is FeC2O4 dot H2C2O4 dot H2O. Let's say I have this species. And in this species, it is acting like a, behaving like a reducing agent. Like reducing agent. If it is acting like a reducing agent, what will be the N factor? First part, what will be the N factor? And second part, if it is an acid, then what will be the N factor? These two questions are very important. So if this entire species is acting like an acid, then only this H2C2O4 is the active species, and it's going to be converted into 2H positive plus C2O4 2 negative. Rest of the salt is going to remain same. So in that case, the N factor will be 2 only. But in case of reducing agent, you know that Fe which is present in 2 positive, carbon which is present in 3 positive, carbon which is present in 3 positive, every species is going to participate. And if they are behaving like an reducing agent, then Fe is going to convert into Fe3 positive, and entire part of the C2O4 is going to be converted into CO2. Now, the calculation of N factor. Both the species are oxidizing, so I have to add the N factor 1 and factor 2. So Fe2 positive to Fe3 positive, changes of 1, and only one atom is there, so you can say 1 multiplied by 1, that is the N factor 1 plus. Now how many carbons are there? 1 2 3 4. 4 carbons are there in plus 3 oxidation state. They are converting into plus 4. CO2 means plus 4. So plus 3 to plus 4, changes of 1, and how many atoms are there? Total 4 atoms. So you can say 4 multiplied by 1. It means total N factor in that case will be 5. I hope this part is clear. So just have a look at it. Then we can proceed for the next part. Okay. Now let's talk about a very simple analysis. Let's say that we have a species which is FeCN6 4 negative. Okay, this species is there and it is converting into Fe3 positive plus CO2 plus NO3 negative, and you have to calculate the N factor, total N factor. What will be the total N factor? So in that case, first of all, I have to decide the oxidation state of each and every part. In this particular case, let's talk about the calculation here. In this particular case, I can say iron is having X oxidation state. Cyanide means 1 negative, so 6 atoms are there or 6 species are there with 1 negative charge, will be equal to total charge which is -4. So X will be +2. So iron's oxidation state will be +2. So Fe is present in +2. Fe is converting into Fe3 positive, means oxidation. Now we have a Cn negative. So how to decide that what is the oxidation state of a Cn carbon as well as nitrogen in case of a Cn negative? In that case, we generally know that this particular part looks like this, C triple bond N. If you know the MO theory, which is molecular orbital theory, then you know how to draw the structure. Otherwise, if you don't know anything, then you can start with the Lewis dot structure. That's it. Then you can draw the structure like what is going to happen in each and every case, and then you will get to know like which species is going to contain a particular charge. So in that case of Cn negative, first of all, you have to decide what will be the charge of carbon as well as nitrogen. So generally we know that in case of nitrogen, it is electronegative in nature. Definitely it's going to have -3 charge. So let's say X or X dash plus -3 will be equal to -1. X will be equal to +2. So carbon will be having +2 charge, X dash will be +2. It means carbon is present in +2, nitrogen is present in -3. Okay. Now have a look at it. This present in +2, this present in +2, and this present in -3. +2 to +3 oxidation, +2 to +4 again oxidation, and -3 to +5 again oxidation. I have calculated these two parts directly. NO3 negative means nitrogen X plus 3 multiplied by -2 will be equal to -1, X will be equal to 5. So that will be +5. So every species is oxidizing in nature. So N factor total will be N1 plus N2 plus N3. So you have to calculate what is N1. So only one atom is there, +2 to +3, changes of 1 multiplied by 1, plus N2 +2 to +4, change is of 2 multiplied by how many atoms are there? 6 atoms are there, plus -3 to +5, change is of 8. How many atoms are there? 6 atoms are there. So if you calculate, that will be 48 plus 12 plus 1. That will be equal to 61. So total N factor in that case will be 61. I hope this part is clear. I hope this portion is clear. Very interesting concept, I must say. Very interesting concept. Okay. Now next part. Let's say that we have a species which is MnO4 negative, and it is converting into Mn2 positive plus Mn6 positive. There might be a chance that this process is given in which Mn single atom is reducing in two different forms. So how do you calculate? So first of all, for these type of reactions, calculation of N factor is not that relevant, because in that case it's better to use mole concept instead of using the concept of equivalence, because in these type of reactions the same atom is undergoing different changes, it's going to form different type of species. It's better to use mole concept. So there are certain limitations of this equivalence concept, or you can say N factor concept. But if somebody asks you like how do you proceed for these type of things, so first question you may ask, is this a balanced equation? So in this case you can see two Mn's are there. So first of all, you should know like how many Mns are actually converting into Mn2 plus and how many Mns are actually converting into Mn6 positive. If you know that particular part from the balanced equation, then you can proceed for the calculation of N factor. So let's say it's already given that 3 MnO4 are there. Among these three, 2 are converted into Mn2 positive and only 1 is converted into Mn6 positive. So first of all, if you want to calculate the N factor of MnO4, then you should know change in first case multiplied by its number of moles, as well as plus change in second case multiplied by its number of moles divided by total moles. That's how you can calculate the N factor in this particular case for MnO4 negative. It's a very interesting case. So if I talk about the N factor, that will be in first case it is changing from +7 to +2. So changes of 5, and how many moles are changing? 2 moles of Mn2 positive, plus from +7 to +6 changes of 1 and only 1 mole is there, divided by total moles which are 3. So you can say that will be 11 by 3. That is 11 by 3. I hope this part is clear. This is the basic idea related to the entire calculation. When a single atom is changing into two different species involving two different amounts. Okay, so that's how you can deal with this entire part. For example, we have another reaction, or just note down, first of all, just note down this entire portion because it's a very interesting hypothesis and a special case of calculation of N factor. So just note down this. Okay, now let's say we have another reaction. For example, I have K2Cr2O7 plus HCl is going to be converted into KCl plus CrCl3 plus Cl2 plus H2O. Let's say I have this reaction and I'm taking this 2KCl Cr2, so this is 2, and Cl, let's say this is 14Cl, 3 2s are 6, 3 2s are 6 and 7. Okay, so let's say this is the equation. Let's say this is the overall equation. And in this case, if somebody asks you what is the N factor for HCl, then the main confusion is that HCl in Cl it is -1. In some of its compounds, it is converting into -1 only. So there is no change in oxidation state. If there is no change, that reaction is non-redox reaction. In this case also it is -1. But in this case, it is converting into 0. So some amount of this Cl negative is actually converting into Cl2. Some amount only. Rest of the amount is having same oxidation state. So in that case, how can you calculate? Again, same type of method. Change in first case is 0 multiplied by 2, 2 moles are there, plus again 0 change multiplied by 2 plus. Now rest in the case -1 to 0 changes of 1. So in this case 1 multiplied by how many moles in this case? 3 2s are 6. So total 6 moles are there. So 6 divided by Total moles in this particular case are 14. So initially I have taken 14. So that will be equal to, you can say, 6 divided by 14, and that will be 3 by 7. So that will be the n factor in this particular case. Okay. So these are some special cases which you should know, like how to calculate the n factor. Okay. Because we have to calculate the number of atoms now. So two atoms are there and 3 moles are there. So total moles of chlorine in that case will be 6. Okay. But there is no change, so I have not included the number of atoms also, because change is 0, so entire part will be 0 only. Okay. Now there is one more case. Let's say one more case. Let's say that I have Cl2. In presence of OH negative, it is converting into Cl negative as well as a ClO negative, and one case which is a Cl2 plus OH negative is converting into Cl negative plus ClO3 negative. So first thing in that case, it's a very important concept. It's the most important concept, I must say. Okay. First thing in that case, first question, if somebody asks you what is the n factor, first of all, what is the n factor and how to balance these type of equations, because this equation is a disproportionation reaction. This reaction is disproportionation reaction. So how to balance this reaction? This is the first question. And second, how to calculate the n factor in this particular case. So I told you that if you want to calculate the total n factor, that will be 1 upon n factor will be equal to 1 upon n1 plus 1 upon n2. Or you can say n factor total will be n1 into n2 upon n1 plus n2. Again, if you solve this entire part, you will get the same part. Okay. Now this is one of the case. So how to balance these type of equations? You can balance these equations with the help of same analysis, which is your oxidation number method. But again, you see that one species is changing in two different oxidation states. In this case it is -1, and in this case it is +1. So how to deal with these type of reaction? In this case it is -1, and in this case it is +5. So how to deal with these type of reactions? So in case of, if you remember, in case of oxidation number method, on reactant side you need one oxidizing agent and one reducing agent. This species itself is oxidizing as well as reducing agent. So for simplicity, can I write one more Cl2? Yes, definitely. Definitely I can write one more Cl2. So what happens? One species will act as an oxidizing agent and next species will work as an reducing agent. So one species is going to be converted into Cl negative and another species is going to be converted into ClO negative. Now I can calculate the N1. Which is 0 to -1, changes of 1, and 2 atoms are there, 2. In this case N2 will be 0 to +1, changes of 1, and then 2 atoms are there, so that will be 2. So if you can directly cross multiply these two, or you can take the minimum ratio, which is 1:1. So there is no need to multiply. Now this reaction is associated with this particular part, so balance this first. So 2Cl are there, so 2Cl should be there. 2Cl are there, so 2Cl should be there. Balanced. Now the reaction is happening in basic medium. So this OH negative generally is not going to occur initially. We know that this reaction is basic medium reaction. So let's start with this particular part. Now in this case you can see 2Cl O negative are there. It means 2 oxygens are there. On oxygen rich side, add same number of oxygen with respect to H2O. So you can add 2 H2O and twice number of OH negative. So that will be 4 OH negative. Now you can see everything is already balanced. If I talk about the negative charge, 2 negative, 2 negative, 4 negative, 4 negative. Reaction is already balanced. So if I talk about the final reaction looks like 2Cl2 plus 4OH negative is going to convert into 2Cl negative plus 2ClO negative plus 2H2O. Okay, you can divide the entire equation by 2 and you will left with only one thing. For minimum ratio, that will be Cl2 plus 2OH negative gives you Cl negative plus ClO negative plus H2O. That will be the final reaction. Minimum balanced equation. Minimum balanced equation. Minimum balanced equation. I hope this part is clear. This part is clear. Now, if I talk about the second type of reaction, again what you can do, Cl2 plus Cl2 gives us Cl negative plus ClO3 negative. But initially, if you see that both ClCl or Cl2 are converting into Cl negative as well as ClO negative. So same species, 1 mole of each, I can say, are involving to convert themselves into Cl negative as well as ClO negative. So you can calculate individually what will be the oxidation number change, or you can say calculation of N factor. But in this type of reaction, now you can see that 0 to -1 same, but 0 to +5. Associate one part with oxidizing and one part with reducing agent. So that is the conversion. That is the conversion. For simplicity, can I calculate N1? Yes, N1 will be very easy. 0 to -1, changes of 1, 2 atoms are there, so that will be 2. 0 to +5, changes of 5, total atoms are 2, so that will be N2 will be 10. So either you can take the minimum ratio or you can take 2:10. So that will be 1:5. 1:5. Okay, now cross multiply these N factor. I told you that you have to cross multiply. So if 10 is there, it means minimum ratio will be 5. So 5 will be here and 1 will be here. Cross multiplying both the N factors. Okay, now this part is associated with this reaction, and how many Cl are converting? So this particular part is 10 Cl. So that will be 10 Cl negative, 10 Cl negative. Now next part, this Cl2 is converting into ClO3. ClO3. In this particular case, you can say only 2 atoms are there, so that will be 2 only. Now again, 3 2s are 6 oxygens are there, basic medium. It means I am adding 6 OH negative here plus 12 OH negative, sorry, 6 H2O, 6 H2O here and 12 OH negative here. Now you can see that we have 12 negative, 10 negative, 2 negative, 12 negative. Reaction is already balanced, but I know that 5 moles are converting into Cl negative and 1 mole is converting into ClO3. Now if you want to calculate the N factor in this case, then change in first case will be 0 to -1, changes of 1. How many atoms are there? 2 atoms multiplied by 5 moles are there, plus next part is a 0 to 5, changes of 5 multiplied by how many atoms are there? 2. How many moles? 1, divided by total moles. If you see, total moles are going to be 5 plus 1, 6. 6 moles are there. So that will be 5 2s are 10, 5 2s are 10, 20 by 6. So you can say that will be 10 by 3, I guess. That will be 10 by 3. No, sorry. For one species that will be total moles are 3. So that will be 10 by 3. No. There is something missing. Okay. Something missing. Let's find out what is missing. So first of all, this is the reaction. This is the balancing part. Now if I combine these two things, that will become 6Cl2 plus 12 OH negative gives us 10 Cl negative plus 2 ClO3 negative plus 6 H2O. But again, this equation is not the minimum balanced equation, so you have to convert it into the minimum balanced equation. That will be 3 Cl2 plus 6 OH negative gives us 5 Cl negative plus ClO3 negative plus 3 H2O. That will be the final balanced equation. That will be the final balanced equation. That will be the final balanced equation. I hope this part is clear. I hope this part is clear. Now if you want to calculate the N factor, in that case I told you that N factor will be N1 into N2. So 2 multiplied by 10 divided by N1 plus N2. So 2 plus 10, that will be 20 divided by 12. So 5, so that will be 5 by 3. That will be 5 by 3. I hope this part is clear. So just have a look at it, and that's how you can calculate the n factor. Okay, so I guess all the cases of this type of reaction are completed, and factor calculation is almost completed for most of the reactions. Now it's time to jump on the next part, which is a concentration term, a very well known concentration term. Okay, so before that, there is a question. The equivalent weight of the salt, which is KHC2O4 plus H2C2O4 plus 4H2O, to be used as a reducing agent. To be used as a reducing agent, not acid. So it means we have KHC2O4 dot H2C2O4 dot 4H2O. Now in this particular case, you know that only carbon is going to participate because carbon is present in +3. It is present in +3. Reducing agent means which can oxidize itself. Potassium is present in +1. Hydrogen is present in +1. Oxygen is present in -2. So oxygen is not going to participate. It's going to form CO2 only if it is acting like a reducing agent. If it is converting into CO2, how many carbons are there? 1, 2, 3, 4. 4 carbons are changing from +3 to +4. So it means N factor will be 4 carbons multiplied by 1 change, that will be 4. N factor will be 4. So whatever the molecular weight of this entire salt is divided by 4, that will be the equivalent weight. That will be the equivalent weight. So how do you calculate this entire part? So we know there is one thing which is just like molar weight. I told you that equivalent weight will be basically molar mass divided by N factor. So in that case, its equivalent weight will be whatever molecular weight it has divided by N factor, which is 4. That will be the answer. That will be the answer, which is option number D. I hope this part is clear. I hope this part is clear. Okay, next part. Consider a titration of potassium dichromate solution with acidified more salt using diphenylamine as indicator. The number of moles of more salts required per mole of dichromate. It's a very interesting question. Don't worry, there is nothing relation with the titration. But if you want a proper explanation related to that part, we can do this question after completing titration. Okay, then again we can come back to this question and try to solve it, but otherwise it's a question of balancing only. It's a question of balancing only. That's it. That's it. Okay, so if I talk about the Mohr salt, first of all you have to understand what is Mohr salt. So Mohr salt is NH4 twice SO4 dot FeSO4 dot 6H2O. Okay, that is Mohr salt. Okay, so in case of Mohr salt, iron is present in +2 and generally it converts into Fe3 positive. Generally it converts into Fe3 positive. Next part is Mohr salt using acidified potassium dichromate. So in case of K2Cr2O7 in presence of H positive, always remember that's going to be converted into Cr3 positive. Always remember, in case of acidic medium, it's going to be converted into 3 positive. That's why it's an oxidizing agent. It's an oxidizing agent in case of acidic medium. But what happens in case of basic medium? In case of basic medium, it undergoes into non-redox type reaction and converts into CrO4 to negative. Again, in this case, if you calculate, it is present in +6. Initially, it was present in +6. So both the oxidation states are same. So this reaction is a non-redox reaction. So you can see that's why K2Cr2O7 is active in acidic medium. But in case of basic medium, it's not going to be an oxidizing agent, but because it's not going to be existed, it's going to be converted into CrO4 to negative. So the species which is active in basic medium is none other than CrO4 2 negative. So I hope this entire part will be clear. So this reaction is non-redox type reaction. Non-redox conversion, because plus 6 is converting into plus 6. So the active species in basic medium is CrO4 2 negative. Active species in acidic medium is Cr2O7 2 negative. I hope this part is clear. So rest of the question, like how to calculate this entire part, that part we are going to discuss in the upcoming section of your titrations. Okay. So this is a very simple analysis. I just gave you the basic hint related to this entire question. Okay. Now, coming back to the next part, for the reaction which is I negative plus ClO3 negative plus H2SO4 gives us Cl negative plus HSO4 negative plus I2. Okay. The correct statement in the balanced equation is this a balanced equation? I don't think so. This is a balanced equation, because the ClO3 negative, which is plus 5, is converting into minus 1, plus minus 1 is converting into 0 in this particular case. So minus 1 to 0 changes of 1, and only one part is there. Plus 5 to minus 1 changes of 6, and so I can cross multiply here. So that will be 6I negative, 1 ClO3 negative. 6I negative means 3I2, or let's try to solve this. Okay, other than writing here and there, let's try to decode this. So we have the reaction which is I negative plus ClO3 negative in presence of acidic medium. It's converted into Cl negative plus I2 first of all. Remaining part we can write down, but let's first of all try to decode this entire part. So in this case, if I talk about the N1, that will be minus 1 to 0, one atom is there, 1. N2 will be plus 5 to minus 1, 6 multiplied by 1, so 6. So cross multiply here 6, cross multiply here is 1. So 6I negative means 3I2, and 1 is 1. Now this is an acidic medium, so it means 3 oxygens are there. What can I do? I can add plus 3H2O on this side and twice number of 6H positive on this side. Done. If that is the situation, if 6H positives are there, then I can say that 6 negative, 1 7 negative, 6 negative, 6 positive, 1 negative is there. Okay, reaction is already balanced. So final equation in that case is 6I negative, but that is the ionic form. 6I negative plus ClO3 negative plus 6H positive converts into Cl negative plus 3I2 plus 3H2O. Now you see some part is remaining, that I have to include H2SO4 as well as HSO4. Main difference between these two parts is only H positive. So if I have 6H positive here, I can add 6HSO4 negative here as well as 6HSO4 negative here, same species. Now these two species are going to combine together and they are going to form the final equation as 6I negative plus ClO3 negative plus 6H2SO4. It's going to be converted into Cl negative plus 3I2 plus 6HSO4 negative plus 3H2O. Now let's find out which statement is going to be correct. So this is the final balanced equation. Stoichiometric coefficient of HSO4 negative is 6. HSO4 negative stoichiometric coefficient 6. Definitely correct. Iodide is oxidized. Iodide is converted into iodine. It means the process is oxidation. This process is oxidation. It means I negative is converted into I2. That is the process of oxidation, because positive charge is going to increase. Okay, positive charge increment means minus 1 to 0. So that absolute correct, that statement is absolute correct. Okay, next part, sulfur is reduced. So there is no function of sulfur in the entire equation. There is no function of sulfur. In case of H2SO4, 2 hydrogens plus sulfur X plus 4 multiplied by minus 2, that will be equal to 0. So X will be equal to plus 6. In case of HSO4 negative, again 1 hydrogen plus X plus 4 multiplied by minus 2, that will be equal to minus 1, because we have charge species. So again, I can say that X will be equal to +6 only. So no change in the oxidation state. So nothing is happening to sulfur. So this statement is absolutely incorrect. Last part, H2O is one of the product. Yes, H2O is one of the product. So yes, definitely this statement is correct. So this is an advanced type multiple answer question. You can see a very interesting question indeed. So you have to balance the equation first. You have to understand this thing and then try to find out the correct answer. Okay, just have a look at it. Okay. Now, in aqueous solution H2SO4, in aqueous H2SO4, the complex diaqua dioxylato ferrate is oxidized by MnO4 negative. For this reaction, the ratio of the rate of change of H positive to the rate of change of MnO4 negative is. It's a very interesting question. First of all, you have to understand that we have a complex of ferrate, which is iron. So this part is actually under the concept of coordination compound. So this question actually belongs to advanced type question. So we have Fe, diaqua means H2O twice, dioxylato is a C2O4 twice, and then ferrate 2. So it means this is 2 positive, this is 0, and this is 2 negative. So 2 negative 2, that will be 2 negative. So and the entire part will be 2 negative. Entire part will be 2 negative. Okay. So this is the thing which belongs to coordination compound, but otherwise this is the complex which is given, and there is a reaction with MnO4 negative. So you have to predict first of all what is going to happen. So this particular part is an oxidizing agent. If you calculate for Fe, let's say Fe is X plus 2H2O. H2O is neutral, so its charge will be 0 plus C2O4. Oxalate is having -2 charge. So 2 oxalates are there, -2. That will be equal to -2. So X will be equal to +2 in this particular case. So iron is in +2. It can definitely oxidize into Fe3 positive plus C2O4. Definitely this species is reducing agent. It's going to be converted into CO2, and in acidic medium it means MnO4 negative is going to be converted into Mn2 positive. So there are few things which you need to understand in case of redox reaction, that MnO4 negative can act as an oxidizing agent in acidic, basic as well as neutral medium. So this MnO4 negative can be converted into Mn2 positive in case of acidic medium. This MnO4 negative can be converted into MnO4 2 negative in case of highly alkaline medium, and this MnO4 negative can be converted into MnO2 in neutral or slight basic solution. Okay, so it can act as an oxidizing agent in different type of mediums. So in this case we have acidic medium, so definitely it's going to be converted into Mn2 positive. Okay, now for this reaction, the ratio of the rate of change of H positive to the rate of change of MnO4 negative will depend upon their stoichiometry. So you have to derive the stoichiometry after balancing this entire equation, then you will get to know, because in this case this entire complex is converting into two other parts, both are oxidizing. So n factor in this case you already know will be equal to n1 plus n2, because +2 is converting into +3 and this +3 is converting into +4 in CO2. So you just have to calculate this entire part and let me know the final answer. Okay, so that's the entire part. Just have a look at it. Okay, now the next part. In neutral or faintly alkaline solution, 8 moles of permanganate anion quantitatively oxidize thiosulfate anions to produce X moles of sulfur containing product. The magnitude of X is. So this reaction is a very interesting reaction. So basically we have a permanganate ion which is MnO4 O4 negative, and it is reacting with S2O3 2 negative. It's going to be converted into it is an ion oxidized neutral or faintly alkaline, that will be MnO2, and in that case the product is, I guess, SO4 2 negative, x moles of a sulfur containing product. I guess that will be the sulfur containing product, SO4 2 negative. Okay, so MnO4 negative plus S2O3 2 negative gives us MnO2 as well as SO4 2 negative. Because sulfur containing product can be this is going to reduce, so somebody is going to oxidize. In case of oxidation, it can never be sulfur, it can never be SO2. It's going to be SO4 2 negative, sulfate ion is going to be formed. Okay, because this is an oxidizing agent and this is a reducing agent. Okay, now the thing is, if I talk about the calculation in this particular case, so N1 will be plus 7 to plus 4 changes of 3. In this case, N factor will be or you can say N2 will be this is plus 2 to plus 6, change is of 4 and 2 atoms. Okay, yeah, definitely that is the correct answer. That's why we have 8 moles initially. So if you cross multiply, 8 will be there and 3 will be here. So 8 Mn means 8 MnO2 and 3S2O3 means 3 to the 6. So that will be 6 SO4. Okay. Oxidized sulfur to produce X moles of sulfur containing product. The magnitude of X will be. So X moles of sulfur containing product. So X will be 6 in this case. So there is no need to balance the entire equation. You can use the N factor only, then you can proceed for the reaction. There is one more thing which I can use to solve these type of questions, which is law of chemical equivalence, which is the law of chemical equivalence. That law is also there. So if you don't want to balance these type of equations, you can use the law of chemical equivalence, which is much more easier, and I can say like here that this law simply says that the number of equivalents of oxidizing agent will be equal to number of equivalents of reducing agent. That's all. But the thing is, how to calculate the equivalents, number of equivalents, that part we don't know yet. So let's try to figure out what is going to happen. But otherwise, you can balance this equation by cross multiplying the N factor according to the oxidation number method. So you can like solve these questions. But otherwise, generally try to use this law multiple times whenever you are dealing with the question of redox reactions. Okay, so this law is very, very useful. Okay. Now, let's talk about the concept of normality first. Then we can calculate what is the equivalent. Okay, so first of all, just like molarity, normality is again a concentration term represented by capital N, which is again equal to the definition of molarity most of the times. So according to molarity of a particular solute will be the number of moles of solute which are present in 1 liter solution. So instead of number of moles of that solute, you can change that part with equivalents. So it is defined as the number of equivalents or gram equivalents of a solute present in 1 liter solution. That's the only difference. So normality will be number of gram equivalents of solute divided by the volume of a solution in liters, and you can say that N will be equal to number of equivalents divided by volume in ml multiplied by 1000. That is another formula for normality, just like molarity. So from that particular part, I can say one thing, that number of equivalents of a solute will be equal to normality into volume, which is in liters. So there is one thing I can calculate from normality, that is the number of equivalents. That is the number of equivalents. But there are multiple things like how to decode this entire part. So first thing, if you know that molarity is basically number of moles of solute divided by volume in liter, that is the molarity. So molarity will be equal to N of a solute divided by volume in liter. From that part you can say that N of a solute will be equal to molarity into volume in liter. So you can see most of the formulas of normality and molarity are exactly same, but instead of using moles I am using equivalents. Now the second part, if you know that a number of moles are basically equal to molar mass, will be equal to given weight divided by the molar mass. If you know this entire part, that is the number of moles. If you remember this exact formula, now in the same way, if I talk about the equivalents, just like the number of moles, equivalents are basically given weight divided by the equivalent weight. That's the only difference. And from the previous discussion, you know that equivalent weight will be equal to molar mass divided by n factor. So can I use this equation? Yes, definitely. So I can say that will be equal to W upon molar mass divided by n factor. So n factor is going to go upward. So that will be W upon molar mass multiplied by n factor. W by molar mass, you know, W by molar mass is number of moles. So you can say that equivalents are basically equal to number of moles multiplied by n factor. I hope this entire part is clear. So this is one of the formula. That equivalents are moles multiplied by n factor. Second formula, that if you know that normality is basically equals to equivalents divided by the volume in liter. If you know equivalents are now basically moles multiplied by n factor divided by volume in liter. You know this concentration term. Moles divided by volume. So you can say from that particular part that normality will be equal to molarity multiplied by n factor. That's it. So this is the relationship between the normality, molarity as well as equivalents and moles. Just have a look at it. Okay. Now just like the molarity of mixing, molarity of dilution. So in case of dilution, you can use the concept of dilution, that is before dilution number of equivalents are equal to after dilution. Okay. Before dilution equivalents are N1 and V1 multiplied by each other. After dilution equivalents are N2 and V2 multiplied by together. In dilution equivalents are not going to change. Before dilution and after dilution both become equal. If you are mixing, then use the concept of mixing, that N total will be equal to N1 V1 plus N2 V2 plus N3 V3 and so on, divided by V1 plus V2 plus V3 and so on. So this is the concept of normality of mixing. That part you have already done. So that will be the normality of mixing. Okay. I hope this entire portion is clear. So let's say calculate the normality and molarity of the following. So we have 0.74 gram of CaOH twice in 5 ml solution. So first of all, I can calculate the molarity first. So molarity will be number of moles of CaOH twice divided by the volume in ml multiplied by 1000. Now I want to calculate the number of moles of CaOH twice. That will be equal to given weight, which is 0.74 gram, divided by molar mass will be 16 plus 17, 34 plus 40, 74. So that will be 74. So you know that will be 10 raised to the power minus 2. Okay, no issues. So molarity will be 1000 multiplied by 10 raised to the power minus 2 divided by 5 ml, 5 ml of the solution. So in this case, you can say that will be 10 raised to the power 2, cancel out each other. So that will be 2 molar. That is the molarity. Now we know that in case of CaOH twice, nothing is given. CaOH twice, nothing is given. So it means it will be Ca2 positive plus a 2OH negative. So in aqueous solution, it's going to give 2OH negative. There is no reaction. So its N factor will be 2. And you know that normality will be equal to molarity into N factor. You can use this equation. So from that part, normality will be 4 normal. I hope this entire part is clear. I hope this entire part is clear. This is the basic idea about the normality as well as molarity. Normality as well as molarity. So calculate the normality and molarity for 3.65 gram of HCl in 200 ml solution. So this is your homework. You can do it by yourself. Very easy question. Very easy question. Okay. The normality of 0.3 molar phosphorus acid. So phosphorus acid is H3PO3. I told you that in this case N factor will be. Try to draw the structure of this acid. So phosphorus double, single, single, single. That is the skeleton structure. 3 oxygens. So 1, 2 and 3. 3 hydrogens. H, H as well as H. It means its N factor will be 2 only. So molarity is given, molarity multiplied by N factor, 0.3 multiplied by 2, that will be 0.6. So that is your answer. That is your answer. I hope this part is clear. I hope this part is clear. Now the next part is the idea about law of chemical equivalence. So law of chemical equivalence can be applied in any type of reaction, which is basically either your acid base reaction or redox type reaction. That's why in titration this entire part is highly useful whenever you are dealing with the calculation of number of moles, or you can say number of equivalents. So basically this simple law of chemical equivalence says that the one equivalent of a particular element combined with one equivalent of other, or in a chemical reaction equivalents or milli equivalents of reactants are equal to the same given amount of equivalents of the product part separately. So that is the basic statement related to law of chemical equivalence. This is a very basic statement related to law of chemical equivalence. To understand it better, we can say that this is the type of reaction we are considering, a very normal type of reaction. In this case, whatever milli equivalents or equivalents of A are there, that will be equal to milli equivalents of or equivalents of B, that will be equal to milli equivalents of M, that will be equal to milli equivalents of N. So entire part works on the law of chemical equivalence. Now, if I am applying that entire part in a compound, which is MXNY type of compound, binary compound, in that case, because these type of questions are very common, binary salt compounds. So, milli equivalents of this entire compound will be equal to milli equivalents of M species as well as N species. That is the basic idea about the law of chemical equivalence. Law of chemical equivalence. One more thing which we can add in this entire part. Sorry, one more thing which we can add in this entire part. So I can say in case of in acid base titration, in case of acid base titration, always remember that equivalents of acid are always equal to equivalents of base. Equivalents of acid or milli equivalents of acid are equal to milli equivalents of base. In the same way, in redox titration, so basically redox titration means we have oxidizing as well as reducing agent combination. So in that case, always remember that equivalents of oxidizing agent are equal to equivalents of reducing agent. I hope this entire part is clear. I hope this entire part is clear. And you know that number of equivalents are basically number of moles multiplied by N factor, first part, or normality into volume in liters, or molarity into volume in liters multiplied by N factor. So these are few equations of equivalents. I hope this part is clear. Now let's talk about the same question which we were talking about in the previous case. This question. So how to solve this question? In this case, you know that MnO4 is an oxidizing agent, and this part will be a reducing agent. So we can say that equivalence of MnO4 negative will be equal to equivalence of S2O3 2 negative. In this particular case, equivalents are basically number of moles, which are 8 in this case, multiplied by equivalents of MnO4 negative in the reaction. So it is converting from plus 7 to plus 4, that is n factor 3. So 8 multiplied by 3 will be equal to equivalents of S2O3, its n factor, which is 8 in this particular case. 8 moles of permanganate, yeah, 8 multiplied by, sorry, equivalents, so we don't know, n of S2O3 multiplied by its n factor in this particular case. If you calculate, so I guess something is missing. So what can I say? First of all, 8 moles of permanganate anion quantity, 8 moles permanganate anion multiplied by its n factor, that is 3 definitely. And in this case, number of moles of S2O3 that we don't know, multiplied by its n factor. So that n factor is basically 8. So from plus 2 to plus 6, it is of 4, and 4 will be there, and that will be that will be yes. So number of moles of S2O3 2 negative will be equal to 3. Yes, 3 moles are there without balancing 3 moles are there. And next part, if you want to calculate for this part, that x moles of sulfur compound are forming in this particular case, so same equivalence of this entire part should form. So from that particular part, I can say that number of equivalents of MnO4 negative will be equal to number of equivalents of SO4 2 negative. Okay, so that part is already known to us, that 8 moles are there and its n factor is 3, will be equal to. Now can we calculate the n factor of this part? So this is plus 6 converting into plus 2, change is of 4 only. So n factor will be 4 multiplied by number of moles of SO4 2 negative forming. So that part will be 4 2s are 8, and n of SO4 2 negative will be equal to 6. So I told you that you can calculate n factor for forward as well as backward reaction. So this is the concept where you can use the backward reaction. Okay. So by use of this law of chemical equivalence also, you can solve this entire question very easily. Okay. I hope this entire part is clear. So that is the basic idea about the law of chemical equivalence. Now, let's say we have the question, what is the equivalent weight of H2SO4 in this reaction? So if I talk about the H2SO4 in this reaction, first of all, what happens, that this sulfur which is present in plus 6 is converting into minus 2, first of all. And in this reaction, this plus 6 is again converting into plus 6. So you know the same type of question which we have already discussed about, that what is going to happen in this particular case if we have the situation when some part of it is going to be converted into plus 6 same oxidation state and some part of it is converting into reduction or oxidation. So you have to determine the balanced chemical equation, and then only you can proceed for the calculation of equivalent weight, because for equivalent weight of H2SO4, the only thing calculated will be n factor. So n factor means you have to calculate what is the n factor of this entire part. Some amount is converting into NO2SO4 and some amount is converting into H2S only. So if I talk about the equation, that equation will be SO4 2 negative plus I negative is converting into I2 plus S2 negative. Okay, that is the entire part of the reaction. So if you calculate this case, n factor will be plus 6 to minus 2, changes of 8, and n factor in this case will be minus 1. So you can cross multiply here with 8 with 1. So 1 here, 8i, so 4i2 will be there. And acidic medium reaction, so oxygen rich side is this 4, so you can add 4H2O here. It means plus 8H positive here. So everything is balanced, everything is balanced in this entire equation, everything is already balanced in this equation. So what can we do? What can we do? So 8I means 8 NaI. If 8 NaI are there, then you can say that 4 Na2SO4 will be there, and 4I2 are already there. Okay, and 4H2O are already there, and S2 negative means H2S will be as it is. The next part is 8H positive and SO4. 8H positive means 4H2SO4. 4H2SO4 will be there. So 4 2s are 8, 4 2s are 8. Something is missing, I guess, in this data. So you can say we have oxygen. How many oxygens are there? So SO4, 4SO4, 4SO4, and 4 oxygens are there extra. If 4 oxygens are there, how many hydrogens are there extra? 2 hydrogens are there extra. But this equation is already balanced. This equation is already balanced. So let's say if I'm multiplying it with 4, then I should multiply it with 4. So that will be 4s and 4s. Sulfur is converting. So 4 and 4s. So 4H2SO4. I can take 8H2SO4. That will be 8H2SO4. If 8H2SO4 are there, it means you can say that will be 8 sulfur, 4 plus 4, 8 sulfur. I is balanced, Na is balanced. 4 2s are 8, 8 balanced. Okay. Hydrogen 8 2s are 16, 16. And in this case, oxygens are 32. And 16, 16, and that should be 16, I guess. 16, 32. Oxygen. This 16. And 16, 32. Arjun Sola 16. No, something is missing in this particular case. Let's try to again do it. So we have the final equation, which is SO4 2 negative plus 8H positive plus 8I negative will give us 4I2 plus S2 negative plus 4H2. I guess this equation is balanced equation. This equation is balanced equation. This equation is balanced equation. So I can break it down as H2SO4 plus 6H positive plus 8 NaI will give us 4I2 plus H2S plus 4H2O. I guess that will be the sufficient equation. I guess Na2SO4. Now something is missing, which is Na2SO4. Na2SO4. So 8 Na are there. 8 Na are there. So I can say Na2SO4 should be there, which are 4. So 4 Na2SO4 should be there. That we have added extra. We have added extra. Okay, because there was a deficiency of Na2SO4. So let's say if let's say this entire part is not present, if that entire part is not present, will the equation is balanced? Will the equation is balanced? Yes, equation is balanced now. So we have a total 4 2s are 8 plus 2 10. So 6 plus 2 8. Okay, S2 negative. If we have sulfur 1, sulfur 1. 4 oxygens are there, 4 oxygens are there. 4 2s are 8 hydrogens are there, 8 hydrogens are there. 8 iodine, 8 iodine. So, and 2 negative charge, 2 negative. So, this reaction is balanced. So, if I am converting this entire part with 2H here and 2H here, so hydrogen should be balanced, na? Something is fishy here. Something is fishy here. So, okay, so let's try to decode this entire part with respect to the original equation, which is H2SO4, H2SO4 plus NaI, NaI gives us Na2SO4 plus I2 plus H2S plus H2O, if that is the equation. So 8I negative, it means 8 NaI are definitely there. 8 NaI are definitely there. 8 NaI are there, so 4 Na2SO4 will be there, because sodium is going to be balanced out. That will be 4I2. 4I2. Okay. If 4 sulfurs are there, 4 sulfur and 1 5 sulfur, so in that case I have to balance three things: hydrogen, sulfur and oxygen. Only these three things I have to balance. So in that case I can say that this number is fixed. This number is fixed. So 4 2s are 4 4s are 16. 16 are there and 4 are there. So their ratio and one more extra is there. So if I can say that will be 4H2O. If I can say that will be 4H2O. So that should be 4 4s are 20 20. So that should be 5H2SO4, but it's going to hamper with this Na2SO4 part. So no, Na2SO4 is correct. 4 plus 1 5, 5 are there. Now in this case 5 2s are 10, only 10 hydrogens are there. 4 2s are 8 and 2 10, 10 hydrogens are there. So this equation is balanced equation. Now this equation is balanced equation with respect to the original equation. With respect to the original equation, now this is the balanced equation. Now you can see, I guess everything is balanced. Now what is the equivalent weight of H2SO4 in this reaction? So first of all, among these 5 H2SO4, 4 are converting into SO4 2 negative same part, but only one is converting into H2S only. So in this case, you know how to calculate, only changes in one. So plus 6 to minus 2, changes of 8, I guess. 8 divided by how many moles are there total? 5 moles, so 8 by 5. So 8 by 5 will be the n factor in this particular case. So equivalent weight of H2SO4 will be molar mass divided by 8 by 5. So that's how you can solve this entire equation. Very interesting question. Very interesting one. Okay. I hope this entire part is clear. Now, next part. Okay, so you can do this question by yourself. A very interesting question. So that will be your homework. That will be your homework. Okay, you can do this question by yourself. Now, acid base titration means you are reacting acid with base to form salt as well as water. I told you only one thing you have to understand, that equivalence of acid should be equal to equivalent of base. That should be the equivalence point. That should be the equivalence point, which talks about the completion, theoretical completion of the reaction. This talks about the theoretical completion of reaction. So that is the meaning of this entire part, theoretical completion of reaction. If reaction is theoretically completed, and you know, it's very easy to calculate the equivalents of acid as well as equivalents of base. So if I talk about the equivalents of acid, that will be equal to number of moles of acid multiplied by its n factor, and in that case n factor will be the basicity of the acid. In the same way, equivalents of base are basically equal to number of moles of base multiplied by its n factor, which is the acidity of base. And you can also convert in terms of molarity into volume multiplied by n factor, or normality into volume multiplied by n factor. That depends upon the given data, whatever is given in the equation. Okay, so just have a look at it. Okay, only two things are there. So I have included certain questions related to the entire part. For example, this type of questions. To neutralize completely 20 ml of 0.1 molar aqueous solution of phosphorus acid, the volume of 0.1 molar of aqueous KOH solution required will be. So in that case, at equivalence point, you know that equivalence of acid should be equal to equivalence of base. Always remember, if the data is given in terms of ml, then you can easily convert into milli equivalents, just like millimoles. So in that case, in case of acid, that will be equal to molarity into volume in ml multiplied by its n factor. That will be equal to the molarity into volume in ml multiplied by n factor. This side we have acid and this side we have base. That's it. So in case of data, you can see 20 ml of 0.1 molar of aqueous solution of phosphorus acid. So we have molarity which is 0.1 multiplied by 20 ml multiplied by n factor of H3PO3. You now already know it's going to be 2. It's going to be 2 will be equal to molarity is 0.1 in case of KOH multiplied by volume which we don't know multiplied by n factor of KOH is definitely 1. So from that particular part, 0.1 is going to cancel out 0.1. V will be 40 ml. So the answer will be 40 ml. So these are the simple questions which can be asked in case of titrations. So C will be the correct answer. You can see, yes, C will be the correct answer. So these are some simple calculations related to equivalence. If you know law of chemical equivalence, then the rest of the part is going to be very, very easy for you. Very, very easy for you. Okay. Now it's time for the redox type of titration. Nothing new is there. Nothing new is there. You can say milli equivalence of titrate will be equal to milli equivalence of a titrant, or you can say that milli equivalence of oxidizing agent will be equal to milli equivalence of reducing agent. That's it. You can say N1 V1 will be equal to N2 V2. You can say M1 V1 N factor 1 will be equal to M2 V2 into N factor 2. So whatever it is, you can utilize that entire part in case of redox titrations also. But what are the types of redox titration? So in question, you may find the reactions with KMnO4, acidified KMnO4, reaction with acidified K2Cr2O7. These are the part of titrations. Acidified KiO3 or KBrO3. In the same way, acidified cerium 4 positive salts or iodine involving titration, which is iodometry as well as iodimetry. So these parts are very important in case of iodometry as well as iodimetry. But rest of the cases are already covered. We have already covered the entire part. For example, I am reacting this MnO4 negative with C2O4 2 negative, which is oxalate ion, in presence of acidic medium. So we know what is going to happen in acidic medium. This Mn is going to be converted into Mn2 positive. This C2O4 is going to be converted into CO2. So that is the only part. You have to calculate their n factor respectively, and the rest of the part is very easy. The rest of the part is very easy. So these are the titrations which are actually there. So if I have included everything in this particular case, I have included everything so that you don't get confused. Okay. I am just looking for a right question. Okay. So let's say this is the question. So 100 ml solution of FeC2O4 and FeSO4 is completely oxidized by 60 ml of 0.02 molar KMnO4 in acidic medium. The resulting solution is then reduced by zinc and dilute HCl. The reduced solution is again oxidized completely by 40 ml 0.02 molar KMnO4. Calculate normality of FeC2O4 and FeSO4 in the mixture. It's a very interesting question. It will require different type of steps, but first of all, we have FeC2O4 plus FeSO4. First of all, try to understand what is happening in this reaction. So in presence of KMNO4 first, KMNO4, you know this entire part is going to be converted. So KMNO4 is an oxidizing agent in acidic medium, which is H positive. So Mn is definitely converting into Mn2 positive. Next part, this Fe which is present in +2, Fe which is present in +2 is going to be converted into Fe3 positive. So that will be Fe3 positive. Okay. Next part, this C2O4 which is the 3 positive is going to be converted into CO2. So these type of reactions you should know, like how to deal with this conversion. If you know this conversion, then rest of the part is very easy. So this is the first step. This is the first step. Now this CO2 is a gas, so it's going to release, it's going to be evaporated. Now second part, the resulting solution is then reduced by zinc and dilute HCl. So what happens, we have now only one thing, which is Fe3 positive, which is present. This Fe3 positive is going to be reduced with zinc in presence of HCl into Fe2 positive, This is the second step. This is the second step. Okay. Next part, which is now this Fe2 positive, whatever resultant is there, it's going to be completely converted into again Fe3 positive in presence of KMNO4, in presence of acidic medium. So the reduced solution is again oxidized completely by 40 ml of 0.02 molar KMNO4. Okay. So this part is entirely converted into Fe3 positive again, and Mn will be converted into Mn2 positive. Okay. Now the question is saying what is the normality of these two solutions, initial solutions. Now let's try to decode. Always go in the backward direction. So last data is that when Fe2 positive is present, because there is no relation with the C2O4. C2O4 is already gone for when it is converted into CO2. So now rest of the data is related to Fe2 positive only. So in this particular case, first of all, this entire component gets oxidized to Fe3 positive iron and this CO2 part. The data of KMNO4 is actually given. The data of KMNO4 is given. So you can say from that part that the milli equivalents of entire mixture in first step will be equal to milli equivalents of KMNO4. Can you say in the first step? Definitely that is for true. So we don't know the mini equivalents of mixture, but we know the entire data. That is 60 ml of a 0.02 molar KMNO4 is there. Okay. This is the entire idea about the KMNO4. Let's say this entire part is present as XML. This will be 100 minus XML, because the entire solution will be 100 ml only. 100 ml only. So we don't know these things, like what is the normality in this particular case. Let's say in this case normality is N1, in this case normality is N2. Let's say. So in this particular case I can say that N1 into X plus N2 100 minus X, that is the milli equivalents of mixture, will be equal to, now KMNO4 is converting into Mn2 positive. Mn2 positive means in this particular scenario, you can say one thing, that the change in oxidation state of Mn will be +7 to +2 means 5. So you can say that will be 5 multiplied by 60 multiplied by 0.02. So 1 0 is going to be cancelled out with this particular 5. 5 2s are 10 is going to be cancelled out with this particular part. That will be 6 only. That will be 6 only. 5 2s are 10. 10 6. That will be 606. Okay. So we have the first equation. That is N1x plus 100 minus x N2 will be 6. This is the equation number 1 from first data. Now second data is not that relevant. because the only thing is that whatever Fe3 positive is there, because CO2 is already gone, this Fe3 positive is going to be converted into Fe2 positive, and Fe2 positive is again converted into Fe3 positive, and this data of KMnO4 is given. So you can say that equivalents of Fe2 positive, or you can say milli equivalents of Fe2 positive will be equal to milli equivalents of KMnO4. Second data. So from that particular part, Fe2 positive is converting into Fe3 positive. N factor is 1. N factor is 1 multiplied by moles of Fe2 positive will be equal to, in this case, milli equivalents of KMnO4 will be 40 multiplied by 0.02 multiplied by N factor, which is again 5. So 5 4s are, so 200 multiplied by 0.02. So this cancel out with this, that will be 4. So moles of Fe2 positive comes out as 4. Moles of Fe2 positive comes out as 4. So moles are there. This equation is there. You can either convert this entire equation in terms of number of moles if you want. If you want, you can convert this entire part into number of moles. But number of moles of Fe2 positive are already there. So this entire part is already with us, or what can we say? Anything else? You can use a normality of this Fe2 positive, but it's better to use this entire data in terms of either you can use the molarity also, molarity of Fe2 positive, Fe2 positive. So if Fe2 positive is there and its molarity is 4, so in this particular data, you can say number of moles, that will be equivalents, I guess. Moles are there, Fe2 positive, moles into N factor, so that will be same, I guess. That will be same. So what can we do? We can say, first of all, we can calculate the molarity from this side into volume. If number of moles are there, then I can say Fe2 positive data will be with us. So first thing is, we have a composition of FeC2O4 plus FeSO4. It's converted into Fe3 positive plus CO2 with respect to KMnO4. Again, it's converted with ZnHCl, which is a reducing agent, converted into Fe2 positive. This entire part is again converted with KMnO4 in acidic medium into Fe3 positive as well as Mn2 positive. Okay. So if these equivalents are given, I can calculate the equivalents of Fe2 positive. If I can calculate the equivalents of Fe2 positive, I can go back into the reaction. So first of all, I can say equivalents of, so that will be, if we have this mixture of FeC2O4 and FeSO4, this entire part is converted into Fe3 positive. Okay, its normality is N1, its normality is N2, N1 and N2, and molarity in this case is, let's say, M1 and M2. V1 is the volume, V2 is the volume here. Okay. So what is happening, that from this data I can calculate this data. From this data, I can calculate this data. Equivalence into n factor, both are same. From this data, I can calculate this data. So I can say that whatever equivalents of Fe2 positive are there in this step, they are going to be equal to equivalents of Fe3 positive in this case. If this is equal, so it means this part we have already calculated. Equivalents are basically n factor will 5 multiplied by 40 ml multiplied by 0.02. So that is basically multiplied by 0.02, so that will be 4. Okay, so that is 4. So this part is 4. This part will be equal to, so 4 equivalents are equal to the equivalents of Fe2 positive from that part and that part. So I can say equivalents of Fe2 positive. So this part is converting into this. So that should be N1 multiplied by X1 plus this part should be N2, and 100 minus X2 will be equal to 4. And in this case, plus 3 is converting into plus 2 and plus 2. Plus 3 is converting into plus 2 and plus 2. So in this case, 1 is converting into, so that will be 4 only. So this is the second equation. So we have the first equation as well as second equation. We have the first equation as well as the second equation. So you can solve these two equations and then you will get the answer. That's it. That's it. So now I guess we have both the equations. Or you can use, instead of this entire part, you can use the equivalents as number of moles of Fe into its n factor. So that is number of moles n1 multiplied by its n factor will be 1, and plus this part individually. So this is converting into plus 2 and plus 2, and these two plus 2 are converting into plus 3. So n2 multiplied by 1 will be equal to 4. So n1 plus n2 will be equal to 4. So we have calculated total moles, and yes, total moles are given. We have the normality equation, then you can solve this equation. Okay, let's try to decode this entire part. And yeah, this is the only concept which is going to happen, because in first case 100 ml solution of this FeC2O4 and FeSO4 is completely oxidized by 60 ml of 0.02 molar KMnO4. So what is going to happen in first case? In first case scenario, that this entire part is going to be oxidized with KMnO4, and KMnO4 is going to be converted into Mn2 positive. Okay, and Fe will be converted into Fe3 positive, but C2O4 is going to be converted into CO2. Okay, that's the first part. Second part, in that case, that after some reaction with zinc HCl, some part is going to be reduced, but CO2 is a gas, it's going to be evaporated or it's going to be gone. Only component will be Fe3 positive, it's going to be converted into Fe2 positive. Then again this Fe2 positive, whatever is present, is going to be reacted with KMnO4 in presence of H positive, that's going to be converted into Fe3 positive and again Mn2 positive. Now the data here is given as well as the data here it is given. So you have to use these two steps only. First part, you can calculate the equivalents of Fe2 positive or number of moles of Fe2 positive in both these species. If you have calculated the number of moles, then normality calculation is going to be very, very easy for you. Okay, so that's how you can deal with this entire question. Okay, from the second data, you can calculate Fe2 positive moles. From that part, you can say the equivalents both are equal in case of Fe3 positive as well as Fe2 positive. So their moles should be equal. If moles should be equal, then again you can reverse back the equation into equivalents. So equivalents of this entire part will be equal to equivalents of this plus equivalents of this, and that's how you can solve this entire equation. Try to solve this equation and let me know the final answer. Okay, so this is one of the good question, advanced level question related to the entire part. Now one thing which remains in this particular case is the titrations involving iodine. So there are two titrations. First of all, we have iodimetry and second one is basically iodometry. Okay, these two things are there, iodimetry as well as iodometry. So basically compounds contains iodine are widely used for titration. Basically if we have iodide, then iodide can be converted first of all into iodine. So if we have a source of iodine, that part first converted into iodine, then iodine whatever is converted is going to react with a very specific solution which is known as hyposolution. So there is one reaction which is common in every type of titration involving iodine, that is I2 when react with Na2S2O3 is going to be converted into Na2S4O6, Na2S4O6 plus again I negative. Okay, this solution, this aqueous solution is actually known as hyposolution, and this part is sodium thiosulfate, and this part is tetrathionate, sodium tetrathionate. So one thing which is very special in these type of reactions, either you can use this direct reaction that you have direct iodine and you can react it with any of the reducing agent, directly. So iodine will be oxidizing agent in this case, or you can first of all generate iodine and then again reacted with this part. So one part is direct reaction of iodine with the reducing agent, and second reaction is indirect reaction to liberate first of all iodine and then its reaction with reducing agent, which is hyposolution. So there are two type of titrations. Okay, so iodide ions can be oxidized to I2 by any suitable oxidizing agent. It means this is the indirect reaction, or you can say iodide ions or iodate ions which are IO3 negative. This is iodate, iodate ions will oxidize to it will oxidize I negative to I2. So this is the oxidizing agent which is going to convert I negative into I2. So indirect step is there, okay. Thiosulfate ions which are S2O3 2 negative can reduce iodine to iodide again. So this is the second step, So most of the reactions involve these two things only, okay. So most of the reactions involve these two steps only, okay. Now you can see in iodimetric titrations, I2 solution directly is taken in burette, and reducing agents like sodium thiosulfate or AS2O3 are taken in a flask, and you can calculate their amount. You can calculate their concentration. These titrations are usually performed in neutral or mildly alkaline solutions to weakly acidic solutions. If the pH is actually too alkaline, then definitely you know that I2 is going to disproportionate into highly basic medium, into I negative as well as IO negative, which is hypoiodite ion. Okay, so that's why we use a neutral type of medium in this reaction. This is the direct reaction. This one is the direct titration. So direct titration of iodine is basically you have taken I2 and reacted with any of the reducing agent, either AS2O3, you can take S2O3 2 negative, whatever it is, and with the help of this reaction is going to be converted into I negative, as well as remaining part of a species is going to be formed, whatever it is. Either it's going to be S4O6 2 negative, or it can be ASO4 3 negative. That depends upon the type of species which is going to form. Okay, so this is a direct type of titration. Okay, so calculation is very easy, that equivalence of this oxidizing agent will be equal to equivalence of reducing agent at equivalence point. So that's how you can calculate the entire part. Now the next thing which is very interesting in this particular case, is the titration which is iodometric titration. So in case of iodometric titration, this is an indirect form of titration. An oxidizing agent is made to react with excess of a solid Ki. The oxidizing agent oxidizes I negative to I2. So there is one extra step, that you initially start with I negative, and then you need a oxidizing agent so that this I negative can be converted into I2. Whatever I2 is liberated is again react with S2O3 2 negative, which is a reducing agent, and it's going to be converted into I negative again. So this is the reaction which involves two steps. So in first step, this data will be missing, oxidizing agent data will be missing, only the data of this thiosulfate will be given. So you have to go back inside the entire titration. From that part you can calculate milliequivalents of this, milliequivalents of this will be equal to milliequivalents of this side, and that's how you can proceed for the reaction. So this is the entire analysis of the iodometric as well as iodimetric titrations. Okay. Now, one thing which I want to ask you, if you want a proper numerical analysis on the analysis on the analysis of titration part, iodimetric, or any type of titration, acid based titration, mixing of questions, back titration, double titration, whatever it is, if you want a separate lecture for this entire part, then just let me know in the comment box. Okay, if everybody wants that particular part, then I'll make sure that we have a separate session for that particular part. Okay, so this ends the concept of titration related to everything. So you can see there are certain reactions that I2 first can be directly reacted with Na2S2O3 to convert into NaI as well as Na2S4O6. This is the direct type of titration. Okay, when it reacts with CuSO4, it means Ki when reacts with CuSO4. So CuSO4 converts into Cu to I2, and I negative will be converted into I2, indirect titration. Then I negative again is going to react with hypo solution to convert back into iodide ion. So that is the indirect part. Again you can use bleaching powder also. Bleaching powder also. So this type of titration can be seen. You can even use MnO2 also. So MnO2 in presence of HCl, concentrated HCl, converts into MnCl2 and Cl2 gas releases. This Cl2 gas is going to react with Ki and it's going to form I2 and Cl negative. So we have created this I negative into I2. Then I2 again is going to react with the hypo solution to convert back into iodide ion, and that's how these type of titrations are going to work. Okay, idea is very easy in this entire case. I have included 2-3 questions also. So try to solve these questions by yourself. If you find any difficulty, if you find any of the difficulty, then just let me know. Always remember that in case of redox titrations, only thing is you need to be very careful when you are dealing with the calculation of number of equivalents, because law of chemical equivalence is very easy, that number of equivalents of one species will be equal to number of equivalents of second species, whatever involved. Okay, so in that case there might be a confusing time that you have to calculate the n factor. So n factor should be very carefully calculated so that you can get entire calculation very easy. But if you want a separate session on numerical analysis of titration part only, then just let me know in the comment box, and I'll make sure that you have that particular session with you guys. Okay, so I guess that's all from my side. We have completed the entire part related to redox reaction. So in redox reaction you can see there is a concept of oxidation number, there is a concept of n factor calculation, and last part which is titration part. Okay, so in titration we just need to use law of chemical equivalence. So I guess that's all from my side, and thank you so much.